Coroutines are the way of working with asynchronous code in Kotlin. They're a powerful abstraction for concurrent systems that make use of intertwined execution, parallelism, and so on. They provide structure to your concurrent code and have a sophisticated error handling system. From helping you get off the main thread to unblock the UI of a mobile application to handling thousands and thousands of requests in a server side app, Coroutines have got you covered. So, let's dive deeper into what makes coroutines special, how to develop a mental model for them, and see how useful they can really be. Today, we're sitting down with Marcin Moskała, who's got a long list of accolades. He's a consultant, contractor, and trainer, the creator of the Coroutines Mastery course, and the author of 6 books about Kotlin. Most recently on our channel, you may have seen him as part of his KotlinConf 2025 talk on coroutines, specifically on debugging and performance tuning them. This is Talking Kotlin. I'm your host, Márton Braun, and I'm joined by my lovely co-host, Sebastian Aigner.
All right. Hi, Marcin. Welcome to the show.
Hello, good to see you again.
First of all, yeah, you are a returning guest, which is very exciting to me. First of all, let me extend a little compliment to you here. I like your shirt. Now, for our audio listeners, at least what I can kind of spot here are like some wings with like and we also see a cup that has the same design. Very nice. Like an orange to yellow hue with a phoenix. That's very cool. Is that your branding?
Yeah, that's a new branding. We have the previous Phoenix, and this is a new one. I was enforced to make a new logo because they told me that the previous one is not modern enough, doesn't fit our new design that we introduced for Coroutines Mastery. But I actually started liking it. I kind of got too used to it, especially since I drink my tea every day in the cup with this Phoenix on.
That's very elegant. I think at least for the cup, you should get one of those special cups where when you pour in the hot liquid, like it actually changes the color or like it reveals the phoenix. Oh, that would be kind of cool.
Yeah, the phoenix should open his wings.
Yeah. Is there a backstory to branding your stuff with a phoenix?
Yes, there are actually a few reasons behind it, but for me the main one is that Phoenix was the symbol of learning. I was a little bit into symbolism in the past, and Phoenix kind of represents the deepest form of learning because to truly learn something, you must let what you knew before die. So this is like a phoenix that is burning to make a space to heat up its children, its new form. So it's like with it's like with our old preconceptions about threads or about RxJava that needs to die to make a space for coroutines.
Oh, okay. That's intense. I'll be honest with you. That's a very intense way of learning. But I guess
that's intense, but it's also very true because one of the biggest problems that I'm dealing with when I'm teaching people coroutines is their old preconception, like those small things like setting up dispatchers IO everywhere on Android, which in nearly all the cases it's not needed, and I mean it's also not a big problem, but it's slowing down our code. And plenty of patterns used on Android, like with using flow for functions that return a single value, is nothing else but just a naive adaptation of patterns from RxJava.
this is very interesting, and I think there's again we're off to a very good start here, because I think there's like the kind of this dichotomy of, on the one hand, to get people started quickly, oftentimes it's necessary to make comparisons to other concepts that they might already be familiar with, but especially when there are subtle differences in how they actually manifest. Sometimes those metaphors are like trying to map one concept to another directly. It can kind of bite you, and it can kind of like, it can give you a foundation that's maybe not as solid as you would like, and then as you build up top on that with more complex constructs, it becomes a little bit difficult. So when you teach people coroutines, do you start them from a metaphor of like something that they might already know? Do you start them from scratch and like, you know, explain it from first principles in a vacuum? Like, how, if someone asks you like, what are coroutines, or like, how should I think about coroutines, where does the explanation start?
So I try to give my own presentation explanation to just like good foundations, and that's actually the first question I ask to my workshop attendees. What is a coroutine? And the most popular preconception is, of course, a lightweight thread, which is, I think, very problematic. I mean, it helps at the beginning because it tells people, okay, it's like a thread, but it's also lightweight, so it's you can use it freely for things that you wouldn't use a thread because you would be scared about the memory use. But at the same time, it is stopping you very much when you need to implement more complex patterns. You know, coroutines are not lightweight threads. Coroutines are a lightweight abstraction that run on top of threads. Yeah, everything needs to run on top of thread. Coroutines are that's actually the definition of a coroutine. Coroutines can be suspended. Which means that when they are suspended, the only remaining thing is their continuation, however it is called in different languages. The trace that allows us to that allows us to resume it, to go back at the point where it was stopped, and references to local state, local variables. In case of Kotlin X coroutines, also the context of this coroutine. That's the only thing that is that remains after a coroutine when it is suspended, which makes it so lightweight. You can have thousands, millions of suspended coroutine, and it's not a problem for you. Each of them costs very small amount of memory, whereas in case of threads, of course, every blocked thread is at least 1 megabyte of memory, which is a significant cost for our machine.
So I think at least in the beginning, when people say like, you know, or when people are taught that coroutines are like lightweight threads, a lot of what you try to communicate with that, or what one tries to communicate with that, is that, for example, like visibility guarantees are very similar, right? Like within a single coroutine, as long as you're not sharing state across multiple coroutines, like you're generally safe. You have like a happens before relationship where, you know, if you're adding something to a mutable map and then you're reading that later on from within the same coroutine, you're actually seeing the changes that were applied. I think that's kind of like, at least a lot of times, why people like to have this mental model of like, well, you know, it's a thing, it runs somewhere, it does need a carrier thread, but overall, like there are some basics that are kind of shared here. So I'm wondering if you have a place where you think that this metaphor like falls apart,
I
or
mean,
if where you're, yeah. Mm-hmm.
The simplest one is that on Android we make most of our coroutines, if not all of them, to run on the main thread, on the UI thread. So that's those two concepts quite clearly contradict each other. If coroutine is a lightweight thread, how they are running on a single thread. I mean, the whole topic
Okay.
of dispatchers gets very confusing when you think about coroutines this way.
Okay, so
Also,
so I understand now that your main concern really isn't with saying like it shares a bunch of properties with a thread. It's if you literally think of them as just another way to create threads that happens to be different, then the
yes.
metaphor falls apart. And
Yeah,
that's why you put the extra emphasis on, well, it's something that always runs on a carrier thread, or well, it's a lightweight abstraction on top of threads, because it implies that you cannot afford to ignore the fact that there are threads and that you kind of need to think about them in certain scenarios as an underpinning abstraction of coroutines. I think I got that part now. Okay.
the abstraction of a lightweight thread makes much more sense in Java when we think about Project Loom. It is still not exactly a lightweight thread, but this abstraction makes kind of sense because those coroutines, Loom, technically speaking, also has coroutines, only they are hidden under the thread. When we block this thread, the coroutine inside, I mean, the stack trace gets suspended, so the stack trace is stored. This the process gets suspended, and another process can run on the same thread. But because this process is hidden behind an abstraction of thread, that at least in my opinion doesn't generate any significant challenges from considering coroutine as just like a thread but super lightweight. Okay. In Kotlin coroutines, it's different. Many of the things we do in Kotlin coroutines would make little sense if we considered coroutines this way. Just think about sequence builder. Yeah, sequence builder has no real concurrency. It cannot be compared to a thread at all, but it is built on coroutines, and it wouldn't work otherwise.
This is kind of an interesting topic, and maybe one that needs a little bit of more diving into, because now I think we're touching at this point where we're talking about suspending functions. We're talking about the Kotlin X Coroutines library, like somewhat in the same part. Do you want to give us like a little bit of overview of like what comes from the compiler, what comes from libraries, what's a like baseline primitive, like what's like an abstraction that's like implemented in like user space or regular code? Want to talk a little bit about that?
Of course, Kotlin X coroutines were implemented to have a minimal amount in the compiler and in standard library. It only includes support for suspension and for basically the support for suspension, suspend function primitives for suspending a coroutine, primitives for starting a coroutine. Whereas Kotlin X Coroutines library have practically everything else. So all the key mechanisms that make coroutines so amazing, so modern, and that make it outstanding in relationship to other languages were introduced by the library. The suspension part is present in many languages. Is present in Go. In Go, every function is like a suspend function. In Kotlin, in JavaScript, C#, Swift, they all have coroutines. It's just that they don't call them this way. The async functions are technically speaking coroutines because they are suspended when you call await on another async function. So they also have a capability to suspend. Yeah? Python has sequence builder, which are also suspending functions. It also has capability to suspend, which is used by libraries using coroutines like async or other libraries. So this core feature of suspension is there in many languages, and coroutines in general are in many languages. But what makes Kotlin X coroutine outstanding is the unique set of powerful features that make it absolutely amazing.
I really like the mention that you gave in the beginning with the sequence builder. Can you maybe just walk us through that example specifically, just a little bit more, because I think it helps underline the separation between like what's built in and like what's like a higher level abstraction.
Yeah. So with when Kotlin received suspension capabilities, standard library introduced this function for building a sequence. You probably have never seen it because it's not very popular. However, it works just like a flow builder. So if you ever defined your own flow with a flow builder, this works exactly the same. It's just that instead of flow, you use sequence, and instead of emit, you use yield. They work exactly the same with just one key difference. Flow builder is based on suspending functions from the bottom to the top. So everything is suspending. So so the consumption of it is also suspending, and so context is passed, and you can suspend in a flow builder. You can make a request to internet which is suspending, or a delay, which you should never do in a sequence builder, because since there is no such a support. Calling a delay would mean blocking the caller. The sequence, you can think of this sequence builder like this flow builder, which is stripped of all the support introduced by Kotlin X coroutines. It is just when you consume this sequence, it just starts this block of code. When you when you yield a value, you just get back to the caller, in line. You just get back to the caller with this value. When a sequence requests another value, then this builder is resumed from where you stopped it, and it continues from the yield that previously yielded value, and continues until another yield, or until the end, which would mean ending of those of this sequence. So has next would return false.
I think this is like one of the like really exciting parts about coroutines in general. And well, maybe I'm reading too much into it, but personally I think it's really an indicator of like the Kotlin language design in general, which is that the team spends a lot of time trying to find abstractions that like generalize really well. And unlike other languages that have like related but different concepts, like, I don't know, async await, and then you have like generators for like your sequences and so on, like in Kotlin, where we're giving you the suspending function as the instance of a like pausable computation, right? And then it turns out that really like a sequence generator, like you said, it's kind of just like a thing where you need to have a block of code that you can revisit at later points, not necessarily concurrently, but just like at a later point, you need to be able to get out of the logic and go back into it. And that's that like fundamental building block that a suspending function as an underlying abstraction provides you, which is really cool. Also, I'm not sure. Do you actually know? Because I think you mentioned that if you would call delay in a sequence builder, like it would obviously just block. I think the compiler even forbids you from calling any suspending function besides yield.
Yeah, right now it is. It does. In the past, it didn't. At the moment, there is an annotation that makes compiler present you with an error if you do that.
Very nice.
Yeah, I actually think that Roman Elizarov, who initially designed coroutines with his team, he made, or they made a really great job. By the way, Roman will also be on our Coroutines Mastery course as an expert. So he made a really amazing job in two ways. First of all, by separating what is essential for building this library, and it was separated for a very good reason, because Kotlin X coroutines was designed for modern use cases and modern best practices, but it might not fit the future use cases. I don't know what future brings us. Maybe programming will look completely different. Maybe we will make some smart contracts or some things that will control agents, and the whole paradigm will change. So we'll need a different library for concurrency. So they designed the best library for current practices, but also left an open door for them or for someone else to create a new library for future use cases. And at the same time, they actually experimented with what different languages offer to us. I remember those experiments. I tracked them. They used this suspension to reproduce all the features from Go, for instance, from all the features from C#. There were those code bases that were presenting how this simple feature can be used to reproduce the concurrency from different popular languages. And in the end, they collected, in my opinion, the gems from all the languages, and they put them all together. And this is the biggest value of Kotlin X coroutines, though those 5 or 6 gems that are here and that are nowhere else in industry right now.
Yeah, I think we see something very similar everywhere around Kotlin, right? like even on the language level, where we have a lot of input from people using other languages, whether inside JetBrains or from the community. And whenever these discussions come up of, okay, let's add this new feature, let's look into this area of like maybe the pattern matching story or like context sensitive resolution to simplify some calls, then the team looks at all of the other things that have been done before, whether it's Swift, whether it's Python. We get a lot of inspiration from other languages and try to build the most cohesive and nicest experience based on all of this.
The one where it all fits together. Yeah, because it's easy to put things randomly in a way that they do not fit each other, like in Scala, and then have terrible and unreadable code. I mean, Scala 3 tries to clean up things, but well, maybe let's not talk about Scala community, because right now there is a lot of controversy there.
All right. So you already mentioned a bunch of other languages that have similar things to coroutines, right? So what do you think sets coroutines apart from the implementations elsewhere? Like what are the features that really make it special and make it work nicely with Kotlin?
So I think the first and the most important feature is, of course, the concept of a coroutine, of a lightweight abstraction that allows us to start things concurrently or asynchronously without worries that that will drain our memory. This is actually present in most languages nowadays. So we have Project Loom in Java, we have Coroutines, async functions in C#, JavaScript, coroutines in Python. This is actually a standard feature. But then we have structured concurrency, which is an amazing feature, an extremely important feature, highly undermined feature. We can discuss it later, but that's one of the things where Kotlin shines. It also shines because it introduced them at the beginning instead of, like most languages, introducing them afterwards, and it's like with nullability. If you introduce it afterwards, it makes little sense. I mean, so in Kotlin X coroutines, it makes much more sense. Then we have dispatchers, which is maybe not that important for backend developers, but it's a killer feature on client, because that actually makes Loom a nonsense for client applications. Even if you could use Project Loom on Android, I don't think it would ever make sense because of the lack of flexibility. We want multiple coroutines to run on the UI thread, but at the same time, it's even better if you can run multiple coroutines run on the UI thread and other coroutines run on the default thread and other coroutines run on the IO thread. That's a killer feature for clients, something that makes Kotlin X coroutines outstanding in client applications. Testing is something that is highly undermined by most developers, but I think that the capabilities that Kotlin gave us for testing coroutines, the virtual time, the run test scope, the simplicity of testing concurrency, the simplicity of simulating different scenarios, that is absolutely outstanding. Some of those features are present in some other languages, not in Java. But they are far away from them for how well it is implemented in Kotlin X coroutines. And the last big feature that I always mention is reactive streams, the flow. So you might say, okay, Java also have reactive stream. It has a reactor right now, previously RX Java 1, 2, 3. So the problem is that reactive streams are based on a completely different mechanisms than blocking functions. So for instance, if you use Project Loom and functions, regular functions, you interrupt threads. In reactive streams, React or RX Java, you cancel, you can dispose or cancel the result of this stream, and this is a different mechanism. The same problem with many other things, with thread management, etc. So in result, if you want to use in one application, like a backend application, you have some WebSockets, so you want to use streams, but you also have some regular requests, you want to use blocking calls. You need to often reproduce or interoperate between those mechanisms. You either make mistakes or it is a little bit overly complicated. So quite often applications decide to, for instance, use reactive streams everywhere, even for functions that return a single value, or which is way more complicated than using suspending or blocking functions. So reactive streams are not good. Overall they are far away from flow that really well interoperates with suspending functions, that builds on all the capabilities that Kotlin X Coroutines gave us, and thanks to that it can be really simple, really intuitive, and work really well.
Right, and I think this brings us to something that I don't think we mentioned so far about coroutines, is that compared to other reactive solutions, they don't make you change the shape of your code so much, right? You can still have natural sequential code line by line without everything being on some kind of special chained operators and the unique API of a reactive library or something like that.
Not everything's a mono.
Yeah,
Not everything's a mono.
I mean, yeah, introducing Reactor is a revolution. Introducing coroutines in most backend applications, I migrated a couple of Spring Boot applications into coroutines. It is mostly just adding suspend modifier here and there. This suspend modifier is something that annoys some people because, okay, you need to propagate it in many places in your code. But some consider that a documentation. It allows us to distinct functions that can suspend. Ergo, maybe they might be started in another coroutine if they can be parallelized. And distinct them from regular functions that are maybe CPU intensive or just making some simple logic.
I think this
So
is
yeah,
also
that's the main difference.
I think this is also a point of critique that we sometimes hear from people actually when talking about Loom, is precisely that, well, with suspending functions, if it has the suspend modifier on it, you kind of have an idea what might happen. Well, the function might suspend, the function might cancel. And with Loom, if your abstraction is just, you run it on a lightweight thread, but your functions aren't marked in any way, then you don't really have an indicator of where things can happen, where your application might spend a significant time like executing, either because it's waiting for IO or because it's doing something CPU intensive. So yeah, the marker functionality of the suspend modifier is actually can be quite useful sometimes.
If I may say, I actually believe that Loom also have a marker, because every function that is actually making blocking operation should throw in Java interruption exception.
Okay.
If it doesn't, it means that someone very likely silenced it, and if someone silenced it, then it broke cancellation in Loom, which is actually an extremely common problem that we don't have in Kotlin X Coroutines. In Kotlin X Coroutines, exception propagation is also based on exceptions. However, even if you catch cancellation exception, it's typically not a problem. In Loom, in Java, this interruption exception is absolutely essential for this mechanism. If you catch it, you just break the cancellation mechanism. And since it's a checked exception in Java, people very often catch it because it's just annoying to mark all the functions as throws interruption exception everywhere. So it's like a super big problem that I know many teams are fighting with. Their developers are catching, silencing it. Sometimes even libraries are silencing it, and without even knowing about it, they just break cancellation mechanism in Project Loom.
What do you mean it's not necessarily a problem in coroutines?
I mean,
Catching a
generally we
cancellation
should
exception?
never catch it, but
Right.
it is you shouldn't catch it. If you catch it, you should rethrow it. However, the costs of that are much less because the coroutine is still in the canceling state. So another suspension should throw it, and even if you don't rethrow it, then coroutine will remain cancelled. There is no such a mechanism as in Java where when you throw this exception, the thread restores its state. In Kotlin X coroutines, of course, you should you should rethrow it. You shouldn't catch it, but it's way smaller problem if you do that.
Yeah, so your code is likely to still recover even if you happen to mess
Yes.
up somewhere with catching one of these. Yeah. I want to loop back to something you mentioned earlier about Loom. That on Android, like it wouldn't help you as much as dispatchers would. This was a while back now, but I I really wanted to jump back to this note. So I think what I understood there is that Loom could only help you run concurrent things within the same UI thread versus coroutines, which can help you get off the UI thread to different dispatchers like IO and the default dispatcher. Is that about right?
So right now, Loom is an executor which has a pool of threads. This pool of threads is as big as the number of your CPU cores, so it's a lot like our default dispatcher. And of course, if you start, you can, for instance, start 100,000 processes on Loom. If they are blocked, they are under the hood suspended. So it doesn't cost us memory. Only those that are active are running on some thread, which actually is a lot like coroutines running on the dispatcher's default. Now, how could we implement Loom on Android? I can imagine. I mean, of course, this wouldn't help us much in Android because in Android we need to do a lot of things on the UI thread. So, you know, that's a different thread. Maybe we could make an executor which would suspend threads when they are blocked, and that is under the hood using UI thread. I don't know if this is possible to implement that. Probably it is with some effort. That could be a little bit, that could be helpful to some degree. Then you could start all the processes, processes that needs to run on UI thread on the executor running on this main thread under the hood, and all the others maybe on the other executor that has a range of threads that could to some degree work, and that would probably to some degree remind us of starting coroutines on the main dispatcher versus starting coroutines on this default dispatcher. However, there is maybe it can be adopted this way, but I just don't see it because there are so many things that we would need to solve. So first of all, using under the hood the UI thread instead of the pool of threads. I don't know. I don't even know if this is possible. The second thing is a synchronous is a way to switch between those executors. I also do not any. I would need to think about it, but I don't see any simple tools. Maybe with
Yeah.
join
So
or
it's
something, but I at the moment I do not see any simple tools that would allow us to like juggle that easily between those two. I don't know.
yeah. So the
Mhm.
so the problem is that Loom is missing this entire switching idea, right? Like
Yes.
this explicit switch from the UI context to some other dispatcher or
To,
some other context.
to, to,
So
to,
it just has a big parallelized thing, but it doesn't allow you to explicitly move off the main thread, move back to it when you need to.
Yeah, I think to some degree we can think of it like coroutines allow us to like switch between different dispatchers that we want to use, which gives us plenty of capabilities, including synchronization capabilities. Whereas Loom is kind of bound to like dispatchers default. That metaphorically speaking could explain that. And yeah, maybe it is to be overcome, but I think there would be a lot of work to change that.
And I mean, on the bright side, with Android being Kotlin first, there already is an abstraction that covers all this with coroutines.
Oh.
I have another question that I'd like to pose here, because we were talking a little bit earlier before the recording, and one of the things that came up that was that you felt that coroutines are quite easy to start with, but they're a little hard to master. So I'm just curious if like there are obviously some basic subjects, like suspending functions, dispatchers, and so on, which I think are quite straightforward. So where do you see people like struggling? What's the point behind like where do you see that step towards mastery when coroutines become more complex?
Yeah, so I actually see it as a huge struggle for many people. I even discussed about it in DroidCon Berlin with one of the attendees where we saw each other. He told me that he just cannot master coroutines. That he spent I don't know, I think he said like 5 months on RxJava, and he felt he mastered that. And I was like, come on, 5 months? You could master coroutines in 2 months. If you investigated that, you could master that entirely. There are not many things in Kotlin X coroutines that you need to understand. The biggest problem is that Kotlin X coroutines hide complexity under the hood. People just use concepts, constructs, thinking they know what they do, when they often do not know what they do. Okay, a simple example is a coroutine scope. You need to use a coroutine scope function to start async functions or launch, but most people do not realize that coroutine scope awaits the completion of coroutines. So they use coroutine scope, launch inside of it, they think that starts an asynchronous process, whereas it makes no sense because this coroutine scope awaits for this launch completion. So it's a synchronous process, which of course lacks, which of course is a result of lack of understanding of structured concurrency. So I believe the problem is that when you use I don't know, RxJava or Reactor, you have it's a much more complicated library, but you can see things that you don't understand. You can see another function that you need to use, and you feel you need to investigate it. What does it do? How does it behave? Okay, there are plenty of such functions, so you just learn them one after another, and finally you start understanding it better and better. You even if you use Project Loom and new Java APIs, for instance, to start a scope, you need to explicitly create this scope. You need to explicitly join it. When you do that, you can feel okay. You can see some constructs. What are they? What do they do? How should I use them? To some degree, they suggest their usage, but they also open a lot of questions. So they go into documentation, read about it. I believe the problem with Kotlin X coroutines is that it's just so easy to be used, so intuitive, that people start using it, but they never verify their preconceptions that they came with. And so they never really investigate, and that's why it's so hard to truly master it.
I think this is I really like that phrasing, because the fact that it's so easy to start with, it is really both a blessing and a curse, right? Like, on the one hand, like, yeah, it allows you to like jump in very quickly, but the problem is that, especially with concurrent programming, developing an intuition just by like squinting at a system running and like attempting to intuit how all the building blocks fit together, that part is very, very hard. So if you don't spend the time to actually like build that foundation to build upon, like it can be you can find yourself in a situation where you're writing code that, you know, it looks straightforward, but you know, for example, but it might not do exactly what you want. Like the classic example for me is, well, if you write your first Ktor application, right? Like all your request handlers, they're all suspending functions and they all run on a thread pool behind the scenes. But that also like very directly implies that, you know, if you have a shared mutable state in your system, then you need to take care of thread safety. And it doesn't say that on the tin. When you know what's going on, when you know that, well, it's executed on a thread pool, of course you have multiple threads accessing the same thing, it becomes quite obvious. But unless you build that foundation just by looking at the system, you might not spot this problem like just from, you know, experimenting in a sandbox.
Yeah.
So here it's really this like this part of, well, you kind of attempt to intuit it when in reality you should just spend a little bit of time building that foundation.
Yeah, I think Kotlin X Coroutines is the best, absolutely best library. If you understand it, you can write things so easily, so quickly, like so little boilerplate code. So that's a huge advantage. It's also a really good library to be read by people who don't really know it, because it's very intuitive. But at the beginning, when people do not know it, it is really to make either a mistake, which is also quite common, but what is even more common, to make things that makes no sense. I can see plenty of them in a project. I quite often review some projects when I work with my clients, and I can see a lot of things that if you have any understanding of coroutines, you can see that they make absolutely no sense. Like a coroutine scope in a function that never uses launch or async, like async that immediately calls await, like different things. My favorite one was when I saw a a shared flow with a reply one, which is conflated and distinct until changed. Like, congratulations, you just re-implemented state flow. Yeah, if you know what you do, you know that those things make absolutely no sense. But since people lack this knowledge, they often do that.
Can we perhaps dive a bit deeper into those specific examples and maybe explain like what the issues are with them? So you mentioned, I think, like 3 things at least. So the having a coroutine scope that's kind of unused, an async await thing, and then around shared flows.
Yeah. By the way, I'm now working a little bit with your colleagues from JetBrains with IntelliJ team, and we are working on introducing some warnings for at least some of those common patterns. But yeah, coroutine scope only makes sense if you start at least 2 asynchronous coroutines inside of it. So coroutine scope is a synchronized suspending function. If inside of coroutine scope you just call another suspending functions, it is pointless. The purpose of coroutine scope is to create a scope and to synchronize the coroutine started on this scope. The second one was
to split up. So it's to split up like one piece of ongoing work that you have into like multiple different.
Exactly. So from the structured concurrency point of view, it's a basic building block that splits and synchronizes the execution of our coroutines, because one of the key idea of structured concurrency is that it should have a clear entry and exit point, just like regular functions, have entry and exit point, or control structures. So yeah, the key concept of structured concurrency, that the subtasks are like nested and are confined within a scope, so that we can more easily reason about them, and operations are not leaking outside of their execution. Yeah. The second one was async.
Before we move on to the second one, I just want to also briefly mention my favorite gripe about talking about coroutines. So whenever you were talking about coroutine scope here, you were talking about a function called coroutine scope that starts with a lowercase c.
Yes.
There's also a constructor function to create a new coroutine scope with a capital C, which is a different thing and is used for something different. Sorry, just in case like someone is on their journey, I just want to make sure that, you know, the intuition that they develop here specifically is for the lowercase c coroutine scope function and not the capital one. And I really wish it was called coroutine scoped, the same way that we have mem scoped in Kotlin native. That's a side story for another time. Sorry, go on with your second example.
I mark it by saying coroutine scope function, and because even though the upper case is also technically a function, it's a fake constructor, and most people see it as a constructor. So
yeah,
that's how I distinct those two. Yeah, the second one is async and immediate await. So if you call async, you start an asynchronous process in relationship to this call. And so await, of course, awaits the completion of this process. So if you use async and straight on that await, and you don't do anything meaningful in between and you call await, that makes no sense. It literally gives us the same result as if you inline the body of this async. Async await only makes sense if between this async and await, you either start another process or you do something suspending, or at least CPU intensive, but rare case.
Yeah. So again, hopefully something that we could check statically and then produce warnings for.
That should be relatively
see if you have
simple.
a statement between async and await.
Yeah, that should be relatively simple. I also know that coroutine scope function without any asynchronous coroutines inside was also considered and can be statically checked. So it will probably have at least a warning in the future. And the last one, was shared flow and state flow. So those are shared flow is a lot like it's like a subject in Reactor. I like to compare it to a mailing list. So you send to a mailing list, and everyone receives an email. This is a shared scope. So a state flow is a shared flow. It literally is, because it implements the same interface that is particularly designed for storing observable state. Yeah, so state flow allows us to, holds some state. It must have some state, so it requires some initial value, and all the coroutines that are observing it, they receive an update whenever this state changes. So it's perfect for observable state, especially on Android, on View model. But it can also be used on backend. It's not that common, but if you have something like, I don't know, a pricing, then you have a WebSocket that observes a pricing from another service, and a pricing that might be checked by multiple coroutines, and some services that might be interested in knowing when this pricing is changing, or a configuration or something like that. A state for that state flow is also appropriate. And state flow, comparing to shared flow, has three key characteristics. It has initial value. It also has some additional API for reading and setting it. It is conflated, and it is distinct until change. So it is not producing updates if the new value is exactly identical to the previous value. So if you reproduce, and it has reply one. So if you start subscribing, you always receive the last value. So if you use a shared flow that and add all those characteristics using flow processing functions, you just reproduced a state flow. So that was the moment when I was it really made me laugh, because such a clear replacement by accident was so unlikely. I couldn't believe it.
Yeah, I think it's one of those things where really you're the knowledge of what's out there and what the library really provides you just really helps you, because then you can, well, if your only tool is a shared flow, then every problem looks like a mailing list. I don't know, but otherwise, if you know that you have a container for effectively a concurrent observable in the form of a state flow, then that becomes probably a little bit easier. A great transition, though, here actually, because we did also want to briefly talk about flows as a reactive kind of programming abstraction. I have some questions about potential pitfalls later on, but first of all, do you want to talk a little bit more generally about flows? You said that there's something kind of special about coroutines as well, and what makes them so useful.
In the Coroutines Mastery, there is over a week dedicated to flow, like 1.5 week. Just
all right, so we can do it in 5 minutes, right?
But I mean, this is a week of small lessons, yeah. So not something that couldn't be presented in an intensive day of a workshop. But generally speaking, there are two key characteristics I would like to discuss about flow, because those two things are mostly misunderstood by developers, especially Android developers, because Android developers in great majority migrated into coroutines from RxJava, and so they used or still use flow the same way as they used or still use RxJava. And so flow is not like RxJava. The key two differences. The first one is something I mentioned already. Flow inherits all the mechanisms from Kotlin X coroutines. So cancellation, dispatchers, exception handling can be discussed in a moment. They are inherited because flow is just a suspend function calling suspend function, which makes it much easier and much better compatible with suspending functions. The second thing that needs to be understood about flow is that a flow by itself is not an asynchronous stream of values. It is just the opposite. It's a synchronous stream of values. There is a way to introduce more coroutines inside of it using functions like buffer, conflate, or callback flow, or hot flows like shared flow and state flow. But flow by default, if you just make a flow off or flow builder, made a bunch of operations with suspending functions in the middle, it would be synchronous. So you could analyze it like step by step how elements flow and how when they are flowing down they wait. Then they can continue, flow, continue. By the way, I have a game for practicing flow operations, and anyone can verify his or her own skills of flow understanding on that. And so it is because of flow implementation. It's also a very important trait of a flow because it helps us with synchronization. Synchronization in flow is very, very simple. Flow operations are very simple. Flow under the hood is just a suspending function calling suspending function. You could reproduce flow in a couple of lines of code. I do that in the course. Quite literally, when you call collect, you call the flow builder, so the lambda from the flow builder. And when you call emit, you call the lambda passed in the collect. That's the end of the description. Everything else is built on top of that. So flow by default should be compared to suspending functions. Now, suspending functions can, of course, start coroutines, and flow can also start coroutines inside of it. They are slightly different because coroutines inside of a flow can outlive the emitting process, but it cannot emit the flow itself. For instance, if your flow consumes from a channel flow or a callback flow, which is quite common because if you, observe a WebSocket or observe some user interaction on Android, it is typically wrapped with some callback flow. So this callback flow runs on one coroutine, and the rest of your flow runs on another coroutine. And there are only two synchronous processes that are communicating with each other using a channel in between. This is actually a very simple process. There is, of course, a cancellation. So if you stop observing, the other coroutine gets cancelled, etc. There are ways to introduce more coroutines. If you, for instance, introduce a buffer in between, there is one coroutine running for everything above, one for everything below. If you use a flat map merge, there is a coroutine. There is another coroutine for every flow created inside of it. So there are ways to create more coroutines in the flow processing. But by default, if you use map or if you use filter, you should consider that there will be only one coroutine going through that, and this will be a synchronous process, which is very, very important because those builders do not have synchronization inside of them. If you looked under the hood, I don't know, in the function like distinct until changed or scan or anything else, it is changing internal value without any synchronization, which is of course faster than if it needed synchronization, but it can do that because of the flow guarantees that those processing steps will be consumed by no more than one concurrent coroutine at the same time.
We should also note here that for those of you who usually listen to the audio version, you might want to join us for the video this time, just for the visual explanations that are happening here as we go along.
The visual
synchronization things.
The visual explanation being hand gestures. It's not like we're drawing diagrams. So
Oh yeah, sorry, I didn't wanna. I didn't wanna.
But the hand gestures are already a win. The hand gestures are already.
Sorry, you stepped into one of the topics that I spent lots of time explaining, and I made many animations on on those. So explaining that even if you scratch the surface, it's just triggering me to give you a deeper and more visual explanation of that.
Yeah, which is why I'm gonna actually hit the break here for a second, because I think that was a lot of things happening all at once, and I just want to try and recap a little bit of what you mentioned here, just to make sure that we're getting the right thing out there and that people aren't the head isn't exploding from all the knowledge we're pumping into it. So flows, if we're talking about regular cold flows, so the ones that are built using, for example, the just flow builder, lowercase flow and then a lambda, they're very simple from the implementation perspective under the hood. They are just effectively two lambdas, the builder lambda and the collector lambda, calling each other kind of in like a ping pong, where you have the emissions on one side, which invoke the collectors, and then as the collector completes, you go back and you continue the execution there. Which fundamentally means that all your intuition, like you mentioned, for a single coroutine still holds. You still have like a happens before guarantee. If you have multiple intermediate operators like a map or a for each, those are an on each. Those all happen exactly the same natural way as you might track them with sequences as well. Where it gets a little bit more complex is when you start introducing different types of flow, for example, like channel flow, which is the abstraction for breaking out multiple coroutines that all collaborate to build the values that are supposed to be emitted to the next operators. And here we have a scenario where you might have coroutines that are started and that are producing values somewhat independently of the actual collector, so they might be running somewhere else, but as the collector or the collection of this flow with potential intermediate operators, as it gets canceled, the upstream flow also gets canceled, exceptions are propagated as you would expect, and so on. Did I get that right? Was that kind of the summary?
Your explanation is perfect. And
okay,
you
very
truly
good.
simplified some of the things. I would like to just add that I have a very simple abstraction to reason about a flow that helps me a lot, that I also present on the course. So the abstraction is that from at the beginning, when you call collect, there goes upstream a request for value. When this request for value goes up, some of the functions are called, like on start, for instance. Yeah, but mostly we are just opening the flows. When we reach the top, we start the production of elements, and we might either have a value. So when we have a value, the value flows down. You might have some delays in the way. Sometimes if you have a filter, you might ignore it and request another value. But at some point, you will consume this value and start a request, not the same request, because previously it was opening that. Now it's requesting another value, up. So this way you can go, okay, a value flows down, give me next value flow up. Value flows down, give me next value flows up. And from up, there are two other messages then that can go. Either a regular completion message, which just completes it, and on the way, for instance, on completion is called, and when we reach the end with a regular completion, we just end this this flow, or an exception, which is also a completion message, because exception completes all the steps. However, it can be you can catch it, then completion will be transformed either into a regular completion or into a value, and then a regular completion, because you can emit before completing. Or if you do retry, if the exception completion reaches retry, we just start the same flow again. So we go up, hey, open again. This makes a difference, because, for instance, if you use on start and on completion above retry, they would, if you have an exception, on completion is called. If you decided to retry, on start is called again. So yeah, this simple abstraction can very easily can help us to reason about flows, even in very complicated scenarios.
Yeah, I really like that, like a visual explanation. I guess people who are more visual thinkers are, well, first of all, those of you watching the video have the advantage, but also just in general, being a visual thinker, I think, helps when it comes to flows, because it's really like the collector trying to pull values through this chain of operators that you have set up, and then a bunch of things happen as you hit the different functions.
I should also add that, as I mentioned, there are some coroutines, and that there are some operators that start new coroutines, and that's everything the same. But then you have one of those processes going in operations above, like in a buffer above the buffer, and one below the buffer, and everything is the same. It's just that once repeats this process for everything above, and one repeats the same process from everything below.
So far we've been, every time I see you gesture, it's always a metaphor for up or down. So I just wanna make sure. So mentally, for you, a flow goes from top to bottom. It doesn't go like from left to right or something like that.
Yes.
Okay. All right. Very good. Well, I don't know. Sometimes, as things progress forwards, we've had a long discussion about which direction the order of the next stations in a subway should be displayed on the screen. Márton, what did you think? You thought the next station should come
forward,
above, right?
You go bottom to top.
Bottom
this
to
is
top.
the way that you're going.
We have it
right?
from left
Current
to right.
station, next stations.
Yeah, I think. Yeah.
Or actually, in Poland, it depends on what direction do you go, because I think it's always the same, and going on one direction is from left to right, and to the other direction is right to left. And the difference in two directions is which of those are, like clearly visible, and which of them are, their alpha is smaller.
Yeah. If you have opinions, dear listeners, on this, you can join us in the Kotlin Lang Slack on our Talking Kotlin channel and let us know. And of course, you can also just generally discuss the episodes there. We're also hanging out there sometimes, so that's always a fun place to be. So far for flows, we've talked about cold flows, channel flows, all these kind of things. Or well, they're both cold flows, but Yeah. But one of the things that I think we needed to rectify in general was when we originally introduced flows in Kotlin, we kind of drilled it into everybody's head. Flows are cold. Flows are cold. But the reality nowadays is that we have cold flows and we have hot flows, right? We have shared flow and state flow, and they are just as valid flows as the other ones. They're not like a lesser category. They just have a different use. Like we mentioned beforehand, we have the shared flow story, which kind of has this mailbox or the mailing list metaphor of like an observable with multiple subscribers, and we have the state flow as the specific abstraction for wrapping a value that evolves over time that can be observed by multiple observers. You mentioned in the beginning, and I did write this part down, that people are sometimes using flows for single value returns, and that there are some mistakes that you're seeing in this like single value return story. Could you tell us a little bit more about that? Because I think there might I don't want to blame anybody, but there might be some listeners who might be making the mistake, and if we can do something to help rectify that, that'd be great.
I'm not sure if I would say there are some mistakes particularly that are a result of this practice, but I just see it way more complicated, because in suspending functions we write a code that we got used to. Just if you want to call something before something else, you just locate it before instead of using on start. If you want to call something after, use it after instead of using on completion. You just make another call instead of using a map. So it's just way easier to use suspending functions. At the other hand, I can see that mainly in Android, and I see at least a couple of reasons why it kind of makes sense to use flows. I mean,
Okay, so before we talk about why it makes sense, please describe the pattern that we're talking about specifically once, just so that people have like a mental model.
So the idea is that generally speaking, suspending functions were designed to be used like regular functions. So functions that make some operations, produce some value, single value or no value, depending on the specified result type, and can suspend in the middle. Generally speaking, functions that return flow were designed for situations where you want to emit multiple values. And that's kind of an expectations on such functions. So for situations where you observe a WebSocket, observe a database, because in Loom you can observe a database, for situations where you observe user interactions like clicks, text changes, etc. Those were, generally speaking, the places where regular functions that return flow should be used. Now, using regular functions that return flow for functions that are within an area of responsibility of suspending functions, so for functions that are just making some operations, suspending once and always returning exactly one result, it is not strictly a mistake, but first of all, I find it confusing that it is blurring the boundaries. And second of all, I just think it complicates our code unnecessarily, because it's just way harder to implement a body of such functions, because you need to consider. You need to use tools and consider things that were designed for multiple values, whereas you don't need. This is all for nothing, because there will be only one value, in fact, under the hood.
So this is for all the scenarios where in my user code I'm defining a function that has a flow, but then I'm actually only getting a single value out of it, or I'm waiting for the first value and then immediately doing something with it. Then it's kind of it's a little bit overkill, because you're bringing all the machinery to do a bunch of things over time, but all you really want to do is like wait for a specific result and then return or navigate away or do whatever you might want to do. And there,
Yeah,
it's
you request a
classic
single
suspension.
value from API or request a single value from database. This is a scenario that suspending functions were designed for, and using flow for that, generally speaking, is introducing unnecessary complexity.
Yeah, that makes sense.
However, I see
confuses-
some reasons behind that in Android. The key reason, I believe, I believe the key reason why people do that on Android is because they come from RxJava and they just map their practices from RxJava into Android. But there is another valid argument that pretty often we need those values to be transformed into a state flow. And of course, flow can be much more easily transformed into a state flow because you just use state in, and that's it. So in some cases, there might be a reason to a practical reason to do that. But as much as it helps in simple cases, I see it more problematic in when your domain grows and when your application stops being that trivial.
Before we continue, just a quick question. Are you okay if we go like 10 minutes over? Because we'd still like to just talk about one topic. I just want to make sure you don't have a hard stop, or you're not like you don't have a rehearsal.
I can spend whole day with you.
Oh, that's so kind. I don't think we'll make you sit through that, but yeah. Okay, sorry, Márton, go ahead.
By the way, I plan to do much more public videos in the future. I started recording videos for the course, and my plans is that next year I want to make lots of YouTube videos, and I think most of them at the beginning will be about Compose. Later, much more of them will be about coroutines because of my cohort course schedule.
Very nice.
Yeah, makes sense. Okay, I do know where to continue from. So the other thing that you might want to keep in mind when you're choosing between a suspending function and a flow right is what it looks like from the user perspective. So for whoever's going to be calling your API, whether that's you just later or other people working on the project, might just get confused by you returning a flow, them expecting multiple values, like you're not clearly communicating the contract of your function at that point when it's returning a flow, but it's only ever going to be a single value. It just doesn't set the right expectations for callers.
Yeah, that's my biggest problem with this pattern. I also think that the boundary should be clear. If you return one result, you should use a suspend function. If you return any number of results, 0 or multiple, you should rather use flow. Unless it's 0 or 1, then you can consider using nullable value or some result. It's this conceptual, or maybe readability or abstraction definition part of our code is often forgotten about by developers who pretty often think very practically. The same problem I can see with structured concurrency, where people thinking about structured concurrency think that it's only about cancellation to cancel the children, cancel subtask, etc. That's of course important, but also the fact that we have a clarity in our code, that we know that if you call a suspend function, that it won't complete without all its subtasks being completed. The observability that you have a clear structure in your application. So if you have a lot of big application with a lot of coroutines running, if you started all of them on global scope, you would have, or if you started a thread on Java, you would have a flat, like thousands of flat processes that you would see no relationship between them. The structured concurrency gives us a clarity, gives us observability, so we can think about a function only in terms of this function. And when we are outside of this function, we know that this function completed because there is a clear entry and exit block. And this nice observability that we already have tools for observing how relationships in our applications happen, which allows us to understand what's going on in this application.
Okay, I think this is a good time to have kind of a more formal definition or explanation of what structured concurrency is for all of those listening and watching us, because I don't think we hit an actual definition so far, but we mentioned structured concurrency and its benefits a bunch of times. So can we maybe establish what structured concurrency is?
So structured concurrency is also quite an old concept, but it was popularized quite recently. The idea compares concurrency, I mean the improvement of structured concurrency to the revolution that we had in programming, where we replaced go-to statement with functions and control structures. So I don't know if you remember that, maybe you do, but in the early days of programming, we have this go-to statement, which means like jump with execution into a specific line. This technically speaking was very powerful. This allowed us to reproduce functions, because you could jump somewhere, execute something, jump back. It allows us to reproduce control structures, so if, to jump over, etc. But it was too powerful, and it made code absolutely terribly unreadable and very, very hard to reason about, because everything could interact with everything else. It also made a lot of blocks pointless. Like imagine try finally, or that opens some resource and then closes that resource. In Kotlin, we of course use block for that. Yeah, you open a file, you operate on this file, you close this file, for instance. Now this makes no sense if you have goto, because what should happen if you go inside of this block? What should happen if you go outside of it, jump outside of it? That makes no sense. And it's not that clear. And of course, the solution was to remove goto and replace it with either control structure like if, when, for, or functions. And all of them has this very important characteristic, that they have clear entry point. Then there is some black box. You can repeat what is inside of it. You can jump somewhere else, execute something, and an exit point. So you jump back and you go, which is essential, because then you can reason about this block like in separation from everything else. I mean, maybe you can operate on some variables, but generally speaking, execution will not go outside of it before it leaves it, which gives us this conceptual abstract block that we can reason about in separation from the rest of our code, which is of course the essence, which is what allowed us to build such a complex systems that we can build nowadays. So it's not that visible, but we have the same problem with concurrent tasks. Let's get back to this use block, or try finally block. Imagine that you open a file, you inside of the block, you start, I don't know, a thread, launch a coroutine on a global scope, some unstructured task, and you pass this file, the reference to this file, to this task. That wouldn't work, because after you started this process, you would close this file, and the thread, the other thread, would try to operate on a closed resource. I know it's a bit of a naive example, but it gives us, it shows us the essential problem that we actually have in many places. And sometimes it is very convoluted and very hard to find it. But when you have a lot of concurrency, it happens. And so the idea of structured concurrency is that it builds relationships, and it organizes our, like if you have a process that starts other processes, those processes are its sub-process, and the parent process is kind of responsible for them. It is monitoring them for their results. It is awaiting their completion, and it is monitoring them for their failures. Let me maybe show you a simple but very practical example. If you want to start asynchronous processes on a suspending function, you of course the correct pattern for that is coroutine scope function, and inside of it async await. Now, why is it so instead of global scope async and await? There are four key advantages of this pattern, of the pattern that we are using. The first one is of course exception handling. If one of those processes has an exception, the scope gets exception, the other gets cancelled, and the scope throws this exception immediately. If this were started on a global scope, if these were threads, well, we should probably see this exception finally because it would be thrown out of get or await, but it might be later because we might first await the previous coroutine or previous thread, and the other thread would surely not be cancelled. This is a situation that we have in C#, in JavaScript, in most languages. Second one is cancellation.
So just to recap, just to recap that first point. So when something fails from all of these subtasks that you kick off, you get the automatic shutdown of all of the other related parts of ongoing work that you have, right?
The second part is cancellation. So if the parent gets cancelled, it automatically propagates to the children, which is very important. If I like this example of a sky scanner that might be a little bit more extreme, but you probably know services like this one. You need to fly somewhere. You open a service like a sky scanner to find a connection from one place to another place. I talked to people who made sky scanner. They told me that every such search cost them a lot of money, at least couple of cents of money. It can be more than that because it of course requires requesting. It takes a lot of time because they are requesting other services and need to analyze that. So CPU, ports, network, everything costs. So it's not uncommon that if you need to find some connection, you open a scanner, but then you realize, oh my God, I made a mistake. I should choose a different date or maybe different city, choose something. So you go back and start another search. So if this were implemented in a pure JavaScript in async functions, by default, in React, by default, those processes would still be running, and the previous search would still happen. The same with backend. Most backends wouldn't cancel that, and those requests, even if connection would be lost, those requests would be still handling, even though no one waits for it. So coroutines give us automatic cancellation. It's very easy on Android. It's absolutely intuitive and used by default. So you just start coroutines on a scope that is associated to some view. So if this view is gone, the coroutine gets cancelled, its children gets cancelled, so connection, the WebSocket connection is broken. Now, if you used coroutines on the backend, then if WebSocket connection is broken on Spring Boot, for instance, or in Ktor, in both of them, that should automatically cause the cancellation of the process. So we should immediately cancel all the processes and free all the network ports, stop requesting close connection to all the requests that we started, which is the best we can have to save resources. The third part is clarity, and something I mentioned already, that you can think about a block of code in separation. Once the function is finished, you can consider, okay, everything it started is finished. And the fourth one is observability. Again, a simple example. Imagine a backend service. You observe it. You have, let's say, at the moment when you captured the structure, you maybe had 100 requests to your service, which started 100 coroutines, and maybe each of them started a bunch of asynchronous processes. So without structured concurrency, we might have thousands of coroutines that were unrelated. Of course, they are waiting for each other and stuff, but it's just not visible. It's very hard to reason about it. Now, with structured concurrency, you should have a beautiful beautiful structure that now can be built with some tools. I mean, it's visible in the IntelliJ debugger, not in the most beautiful format. There is also a plugin that can be used to display it in a nicer form, and then you can nicely analyze. Okay, each request may be having a context, some identifier that allows you to identify what call started this coroutine, and then from that you can see what is it currently doing, what are the sub processes it is currently executing. And yeah, that's also an advantage, especially in bigger systems.
Let me give shoutouts to, I think, 2 KotlinConf talks here, which are related. We have a talk about how we've improved the debugger UI and just general debugging of coroutines in IntelliJ recently. I think that's from this year.
Yeah, I loved it.
And then
It was
you
really
also
good.
mentioned excellent. And we also mentioned the Ktor scopes that you get to, again, like manage all of your concurrent work. I think a talk about that was also at KotlinConf maybe last year. We'll make sure to dig those up and put them in the description for anyone who wants to catch them.
Márton, did you have something? Because I got boatloads.
You go.
Okay. First of all, you mentioned, and I think this was one of the mind-blowing parts of me exploring web development once again more recently, and it really goes to show that your previous experiences very much inform a lot about how you think about like developing a system, which on a meta level, before I even get into the details, is the reason why you should try different things and like, you know, actually like take a look at the grass on the other side of the fence and, you know, observe its color. One of the things that Márton's face palming. Yeah, one of the things that really blew my mind was knowing that even when you are using like some of the slightly higher level abstraction frameworks for making requests in React, they typically don't integrate with like the React lifecycle in the same way that you would expect to happen in, for example, Compose, Jetpack Compose multi-platform, right? Because we typically do launched effects to start some kind of side effects, and launched effects have the property that as a composable gets rid of the or exits the composition, everything that happens inside there gets canceled, which means, you know, if you're making a long running network request or you have a WebSocket open as part of this, all of that gets closed, all of that gets tied down. The equivalent of this in the React world is doing a bunch of like abort controller finicking around, which is not out of the box. Like having out of the box some sort of effects does not necessarily wire it into the cleanup logic, which, or it does not automatically hook itself so that when the component gets removed, you clean up these tasks. And interestingly enough, what surprises me so much, and what really is surprising me in the web world here, is it's much more needed in the web world, because when you're in a browser, all modern browsers they limit you to like 20 concurrent like HTTP requests at a time, maybe 20, maybe 40, I'm not sure, but like a 2-digit number of requests at the same time. So if you have a component that by itself makes a request and you're loading like 100 of those in a lazily scrolled list, by the time that you've scrolled like 50 components down, if it takes a while for those to finish, the new components that pop up on the screen, they'll just not provide any information until all the lazy stuff that you're not even looking at anymore, until all that's loaded. I'm very much hoping that at least this was my experience, even when using something like React Query. They do have integrations, but they require you to do a bunch of manual setup. If someone from the web world wants to correct me on this, I do wish to learn more about it, but I was just surprised by the lack of convenience, or well, the presence of convenience that we have in the Kotlin ecosystem for all of this.
Yeah.
Yeah.
I would say that in Compose, at least in applications, we primarily start things on a view model scope. But yes, automatically both view models, when they are cleared, they cancel view model scope, and components, when they disappear, they are detached. They are closing, canceling scope from their effects.
Yeah, so in this scenario, it's just a matter of like fine-grainedness, right? Like you might have something that's attached to a component, or it might be attached to a screen that has a view model, which you still navigate away, and it has a life cycle. And upon getting popped, like you still want those things to be canceled.
So for your cancellation to work fine, you just have to stop yourself from doing stupid things, and it will work automatically.
This is most of coding, right?
Yeah, I think that's good advice. Like
Yeah,
just for life, just don't do stupid things, and things will work fine.
Yeah. Now about JavaScript, I believe the key problem is that async functions just do not support cancellation, as far as I know, and it's just yeah, it's not there. So as far as I know, most at least the project that I cooperated with worked substituted that with using RxJS, which again is overly complicated. It has cancellation mechanism that it's quite complicating our code, and I don't like it.
I was really just so surprised that, well, I get your point with async functions not having cancellation support out of the box, but I mean, when you're building React apps, you're already operating on like one layer of abstraction above like just writing plain JavaScript. I was just very surprised to, with the high level stack of like libraries upon libraries upon libraries, that no one in this stack had already given me like a nice integration point that would just plug in like Lego and get me these things out of the box. I am talking from a slightly more amateurish position here on the front end, though, so I'm happy to be
as far as I remember, a specific async function can be cancelled, but it is its behavior. This cancellation has limited effects, and it definitely doesn't affect the async function started inside of it. So we could probably reproduce it with some code, but that would require a lot of effort in all our async functions.
Yeah, and like looking at it here, I'm looking at TanStack query, for example. You do get an abort signal instance, but that means that your fetch implementation, or whatever, your Axios implementation, still needs to wire this kind of stuff together. And all of the samples that I'm seeing here are like 20 lines of code, which is, I mean, it's not going to break your neck in a large application, but if you could avoid writing those, that would be kind of nice. That's all I'm saying.
To reel this back into the Kotlin context, there is one more like compose API that we should really mention here, which is collectAsStateWithLifecycle, which of course also does a lot of really useful cleanup for you, so that you shut down processes, especially observing flows when it's not needed. Ties it really nicely to lifecycle in a multi-platform aware way if you're running on Compose multi-platform. And this, you won't be shocked at this point, is also one of the KotlinConf talks that we had this year. So we'll also have that one linked in the description.
Wow.
I actually thought it's obvious to everyone, but well, maybe not. That collect a state with lifecycle is a standard way on Compose to observe state flow.
So zooming back out to the structure concurrency here for a second, I really think you made quite a nice metaphor, I think, overall. The concept of going away from goto and moving to like if statements, it holds in a bunch of different ways, because not even just like being able to reason about each building block individually, but also being able to reason about the program as a whole, because all of a sudden it turns from like a spaghetti list of just instructions to something that, well, in regular programming, it's your it's like your syntax tree, effectively. Like it's which basic blocks. I always, for me, the metaphor here is, it's kind of from like the disassemblers from like IDA Pro and stuff, when you can kind of see like an arrow of a basic block of like a bunch of instructions, and then you have like a comparison, and it might hit two other blocks. Like it's a typical kind of flowchart interface. And you have quite literally the same, like you get the same flowcharty structure when you use coroutines as well, with coroutine, like with the coroutine scopes. Like you said, you get this parent and child relationship. I personally would always I wish that we would actually not call it structured concurrency, but more specifically, I would love to call it tree structured concurrency, because that's really the structure that we're building. We are building tree structures. It's always a parent with multiple children. That has a computer science term. It's a tree. You can't have more than one parent. Well, like no more than one direct parent. You can have multiple children. You have a root, you have a bunch of children, that builds a tree of coroutines. And then I think all the metaphors also make a lot of sense, right? You have cancellation, like you just snip off like one part of the tree and the entire thing falls down. Or like one thing that's all somehow related, like something breaks, and then of course all the other things that are directly related, you got to take those out as well. Like you prune the tree where it makes sense, and you kind of get the logic about where you're allowed to, or where things are supposed to be automatically like snipped off when things go wrong. So I'm really on this. I'm on this tree metaphor.
I cannot emphasize enough how visual this episode is. If you're missing out on all the hand gesture explanations, please watch the video version.
I am doing a lot of like snip, and like just pretending to throw up visualizations that don't exist.
I don't know where the name came from, but I have a theory. I think it's very likely because at the beginning, this feature was very much compared to this GoTo that I mentioned already, and of course the solution to GoTo was was the control flow. So we have a control flow and control structures. Yeah, sorry, the control structure. So control structure is a formal name for all the if blocks, when blocks, for loops, etc. So control structure is something that structures our control. Yeah, why control? Because the control flow is a formal term for how our how the execution of our program goes in our system. So I think that was the reason we have a we have control structures for controlling how our for structuring how our control goes. So I think we also have structured concurrency for controlling or shaping how our concurrency flows.
Yeah. I still think that the tree structure specifically really it's a helpful metaphor for learning. I mean, we're already over time, so what's a little bit more? I have an interesting question for you. The Márton's face palming again for our audio listeners. I here's something. So I've also been teaching coroutines for quite a while, and one of the things that, when presented in a vacuum, sometimes confuses people is the relationship between coroutine scopes and coroutine context, which always kind of surprised me a little bit because they're fundamentally very different concepts. They have some relationship, but they kind of have a fundamentally different aspects. Do you want to talk about that a little bit? I don't know if this is an experience that you've also made, perhaps.
I have never I haven't seen this particular confusion. I definitely see the confusion between coroutine scope function and coroutine scope builder.
I mean, they're literally called the same. I think that's very, very fair to be confused.
So, yeah, coroutine context is a much more lower level abstraction because that's what it is. What is attached to every coroutine, and that's what also is inherited by children coroutine. So every coroutine has context, and every children coroutine by default inherits context from a parent, inherits everything from it, except for a job. So that's a coroutine context. Coroutine context has many purposes. The most popular coroutine context is, of course, dispatchers, which decide on what thread or pool of threads coroutines should be running. But you mentioned, I mentioned backend storing some data about requests. That's also a common practice that that we attach on backend some information about requests that started this coroutine. Thanks to that, this context is passed down to other coroutines, and it can be used either for checking permissions of the caller or for enriching our logs when we are when we want to have a bit richer logs. So logs can include an information what user or what request actually led to this particular log. Whereas scope is much more higher level context. I know why they can be confused, because a coroutine scope interface is an interface with only one thing. It's a coroutine context property. So coroutine scope looks a bit like a wrapper over coroutine context. But conceptually speaking, it's a very different concept, because coroutine scope in this tree of coroutines is can be considered like this node on this tree. So so you need to create a scope to make a root of this tree, coroutine scope with the builder to make a root of this tree, and then every coroutine that you start on it creates its own scope. Which allows children to be its children actually. So when they are started on the scope of a parent, they inherit everything except for a job, and they use job as a parent for their own job, and this way relationships are built.
I think that's exactly kind of like the key differentiation. I think it's just when people first get started and you don't really have an intuition for the terms themselves, you know, they're both kind of things, and they're both kind of like available as like variables in scopes, or you know, you can access them, you can call things on them. Sometimes I think the differentiation that people have for them is just not so clear. But like you said, once you kind of you get into the depth of it, it becomes pretty clear that like you have the context, which is just kind of like a map of configuration options that are associated with a coroutine, and then you have the scope, which is the component used to build this structure of well, in this tree form, which are fundamentally, like, once you understand what they're each used for, I think the confusion becomes or yeah, that alleviates the confusion. Yeah, structure concurrency is a fun topic.
Of course it is. I mean,
somewhere
I think it would. I even created a call for paper for a presentation, particularly about structured concurrency. I think I could fill a whole presentation presenting the concept and the consequences of this idea. By the way, the idea got popularized by Python library, which is not very popular. I think it's called Trio. And I remember when I was searching that, they have a whole part of a forum only dedicated to structured concurrency. And what kind of surprised me is that the discussions there are alive, you know. So there are people discussing very concretely the concepts of structured concurrency, kind of in separation from a technology. So there is so much to be discussed in the conceptual level and in the implementation level of this concept that you can have numerous discussions about it.
I just looked it up, but unfortunately, it's spelled trio in the traditional sense. I was really hoping that we just got a trio, and I had one more time, you know, the concept of trees involved.
But I guess it might be related to the tree structures, because over there, structured concurrency is not only possible, but it is required. As far as I remember, you cannot start coroutines that are not structures. I mean, in Kotlin X coroutines, Technically speaking, also don't, because you need to start anything on a scope, but you can always inject a scope, like a background scope, application scope. We do that and start something on it. Yeah, we sometimes do that. Whereas, as far as I remember, this library is much more restrictive and enforces everything to be structurally concurrent.
Okay.
All right. One of the topics that you mentioned way in the beginning was that coroutines also play nicely with testing. And I think you also mentioned that, of course, this is something that developers often skip, but actually, it works quite nicely when you get to testing your coroutines. So before we wrap up, at least in a few minutes, let's try to talk a bit about testing and how that works with coroutines,
So-
just like we would do at the end of a project, I guess.
So in Kotlin Makes Coroutines test, you have tools for operating on a virtual time. So when you operate on a virtual time, so when you operate on a you typically use run test that operates on a test scope, that operates on a standard test dispatcher, that uses test scheduler under the hood. Nevertheless, whenever you operate on this dispatcher, that like test dispatcher, all the delays that you make, they don't delay your coroutine on a real time. They just schedule it to be executed at certain point of this testing scheduler virtual time. So the real time doesn't matter for that. It's just that there is a hook. Okay, once virtual, like at this moment of virtual time, this coroutine should be resumed. And this simple capability gives us a very easy way to test things that are not tested in most libraries. So let's just get back to this very, very simple example, suspending functions that uses coroutine scope, async, await. You might wonder if this function is actually starting to things asynchronously, which is not that obvious because, as I mentioned, many people make mistakes and maybe make async an immediate await instead of postponing this await after async blocks. So you might want to you might want to check it. You might want to protect it because you might be worried that some of your colleague will change this behavior in the future. And that can be done very, very easily using this virtual time. You just start your test in the run test. In your fake or mock, you just add some delay. And let's say delays. Let's say you give each of them, or maybe you give one of the calls delay X and the other one delay Y. And then in your function, you can just add an assertion that the current time is this virtual, is this counter of a virtual time. So it gets the current moment of time from this scheduler, and that the current time is a bigger of X and Y. Yeah. So if each of them should take 1 second, if they are executed asynchronously, the current time should be 1 second. If these were implemented incorrectly and they were executed sequentially, the current time would show us 2 seconds. And that's a very, very simple example, which of course makes, I mean, it also makes sense in this case. It's a very simple addition that costs us nothing because such a test is immediate, yeah, because it doesn't really wait any real time. So it's a simple improvement that that costs us nothing. But it makes even more sense when you have complex scenarios where you really don't know if what you implemented behaves the way you think it behaves. So if you have a complex functions, maybe some flows that start some asynchronous suspending operations inside, and you want to make sure that the not only the outcome, the result of that, but also the timing, the time when elements are emitted is as you expected. Of course, for that you would also likely use a turbine observe this flow, but that's another topic. And it also gives you a way for testing even more complex things that are rarely tested, but in some complex systems that might be very useful. Imagine that you have a complex process. Someone make an order, and this order starts a bunch of processes, like it requests making an invoice, it requests sending this order, create something on different services, and the results of those services, what they return to you, if they succeed or not, influences the whole process. And you want to verify scenarios. What would happen if this process responded first, but with a failure? Or what would happen if this process responded first, then this, and then the other one? So such scenarios can be very, very easily implemented, simulated by just using different delays. You can just use mocks or fakes with configurable delay time, and you can simulate any kind of scenario that you want, which is something that, as far as I know, I mean, if I wanted to do that in Java, I don't think there is a way to do that without making it wait a real time, which always generates problems. Yeah, like first of all, makes our test take a lot of time. Second of all, then you start your test on CI. It's a slower computer, maybe some disruptions, then your tests are failing randomly. That generates plenty of problems, which in Kotlin Coroutines we don't have, because everything is perfectly predictable, and the machine you are using, the real time, plays no role in the outcome that you will see.
Yeah, I think the main advantage really is that you get to have really fast, basically instantly running unit tests, while in virtual time you get that fine grade control over delays and when things are happening.
So still a couple of things here. I always love to nerd out about a little thing, which is Lincheck. I just want to shout that part out. For those of you not familiar, that's a library that we're developing at JetBrains Research, specifically for concurrent development. That was originally designed to test concurrent data structures, but we've expanded it to also just test generic concurrent code now, concurrent application code. It's very cool. So like Marcin, like you said, when oftentimes you can write really cool tests for using virtual time. If you are writing some slightly lower level code that needs to, for example, make sure that thread synchronization is right, or that you never get into any race conditions, Lincheck is kind of a cool thing that's coming out of our research that you can use to work on that as well. I don't want to spend too much time on that, because we are pretty long on this episode. But you did very briefly, just like on the side, through in like if your testing flows, you'd probably use a Turbine. What's the deal here? I assume you're referring to the library from Cash App,
Yes.
and not like an actual airplane turbine, I hope.
Yes, and neither ones used to generate electricity. So that's just a popular library. I wouldn't say you have to use it. I used it in some projects. In other projects I implemented my own functions, because this library is actually pretty simple, and most of that can be reproduced with couple of extra lines of code in every test. So this is a nice library. It has some advantages, it has some limitations. It just allows us to consume values from a flow. So you instead of I don't know, collecting on a flow, which would mean awaiting the completion, which pretty often would make our test run forever, because most flow starts from some cold flow, hot flow, and so they never complete. So this is like a collect. This is like a collect on a scope on a coroutine. And that allows us to access the results. So with this turbine object that is returned, you can await next value, next item. You can check if there were no other errors or no other items in between. It's a nice support. To some degree, it can be reproduced by on each that is adding to some results collection a result of success, catch that is adding to some collection result of failure, and launch in background scope from run test. So that's a replacement that I sometimes use, but then using that is of course a bit harder because you need to advance time and instead of awaiting item and then checking what is there. So Turbine gives some nice features for testability. It also has some limitations that I can also see.
Yeah, but I think overall it just provides this like out of the box abstraction for precisely this for decoupling the emitter from your test in a way that makes it possible to look at the structure of the output, await new elements, wait to make sure that you can also check conditions like an empty flow or that the flow finalizes after a certain number of elements, all these kind of things. So it's a small library. I think you can fit the entirety of its API surface on a single slide, depending on the font size, I suppose. But you can get it up there. So it's just something that I think people can look into. Yeah.
Yeah, it basically just sets you up with a lot of good defaults for collecting the values from a flow. Okay, I think we're about to ready to wrap, but of course, before we do that, let's talk a bit more about your upcoming course, Coroutines Mastery, if I got that right, because we already mentioned that a couple times. So let's briefly explain how that works and what people can expect if they want to join that.
Yeah, thank you. So actually, this comes from my experiences. You probably know that I'm also a trainer. I'm a partner of JetBrains, so we are in that together. And one of my most popular workshops is about Kotlin coroutines, but I always had this problem because Kotlin coroutines is a complex topic. I mean, it's not that wide. I can explain all the concepts in 2 days. The problem is that people cannot comprehend all the concepts in 2 days. I typically I was typically teaching it in a 3 days form, where I could go a little bit deeper into each of those topics, and we had more time for exercises. But still, it's like 3 days is enough to cover everything, to even practice practically everything, but not enough to truly integrate that, not enough to reflect on how it relates to your code. It is just too little of a time for people, and at the same time, I also feel any other resource materials are not better in any way. People, as I mentioned already, are not educating themselves too much about coroutines. It's so that was a problem that I was facing throughout years, and I conducted many workshops about Kotlin X coroutines. I think it could be around 50 editions of course about coroutines since they were in beta, and I thought about a better formula for a very long time, and I finally found it. So the idea is to make a cohort course. You can think of it like a like this, let's say 3 days course, but split it into small lessons and divide it into a range of 4 weeks. So every day you receive a small lesson with an exercise. Additionally, I mean, those lessons are a bit better prepared because it's prepared in advance. There are also additional exercises that are not necessary for a certificate, but if you want to go deeper into a topic, you can make them. There are also additional lessons. I added plenty of lessons about patterns on Android and patterns on backend. But essentially a small lesson every day. And to give a space to process that, people have enough time, so for 4 weeks, where they can finish that, and they can relate it to their project, and where they can discuss it, because as a part of this course, we also have a discussion platform, a circle, where we will have everyday discussions. We'll have Q&As. There will be Q&As with me every week. There will be also Q&As with other experts. So I can already confirm that as an expert, we'll also have Roman Elizarov, who was the initial designer of Kotlin Coroutines, and Vsevolod, who is the current head of Kotlin Coroutines team. And we'll also have other things. We'll have games. I made 2 games for this course. So some of the exercises will be to reach a certain level those games. This is what I think is the most effective way of learning about it. You have time to think about it, to reflect that. It's not too intensive, so you can easily connect it with your daily work. You can do it after work, during work, on weekends, however you want. It's also more comfortable for companies, because they do not need to reserve 3 days off without all the developers in the team. You can just you can purchase them workshops. You can purchase them this course, and they will be following that with a group. They can have their own discussions. Whoever is purchasing that can also ask us to have access to their progress. We have this feature. The company can see how many exercises were completed by people. Oh, there is also review. So every exercise will be reviewed by me. So every exercise solution will be reviewed by me. And there is something that I think will make you pretty happy, because I also wanted to make a final project. I was thinking about it for a long time, and I decided to give a freedom to people of what they want to do. But I decided this final project should be something social. So anyone can do whatever he or she thinks will be best, but it must be something for the community. So you can write an article, you can publish a library, you can create an example project, something related to coroutines, but you must do something for the community. And I will, of course, review all of them. And you can do that throughout the course, but the last 5th week is dedicated to working on this on those projects. And also this last week is for reviewing the most important topics, a high-level perspective on what's covered in the course. So yeah, that's the plan. It starts in this November, at the beginning of this November. Another edition will be next year, so there will be only, just like with conferences, only 1 edition per year of my cohort courses.
All right. Yeah, we hope that a lot of people can deepen their knowledge of coroutines through this course. That sounds like a great opportunity to do that. So thank you so much for joining us today to chat about coroutines, especially for staying over time. This is going to be one of the longer episodes for sure.
My pleasure.
I think we covered a lot of topics today. So whether people are using coroutines, but they're at the surface level, and maybe we've inspired them to look deeper into coroutines, or maybe they're using Kotlin but not migrated to coroutines yet. Hopefully we inspired more and more advanced coroutine usage as well. I know that we'll have a lot of links to things in the description. We touched on a bunch of talks, probably documentation, libraries. We'll make sure that all of that is down there for further research. And as Seb already mentioned, if anyone wants to give us feedback or chat about these topics, we welcome them in the Talking Kotlin channel on the Kotlin Lang Slack. With that, I think we're done with this episode. Thank you everyone for joining us today and listening to us talk about coroutines for roughly 2 hours.
Yeah.
We'll see what the final timestamp is. And yeah, see you next time.
Thank you very much.
Thank
Take care,
you.
everybody. Bye-bye.